And I hope you can all see my screen now. Okay, great. I will try to keep somewhat of an eye on the chat, but it's always hard to monitor everything. So please don't hesitate to unmute yourself and just speak up if there's a question or comment you have. So I want to begin by just thanking Veronica, Grayson, and Anna for the coaching. They listened to a practice talk, and their tips went way beyond simple tweaks. I think they really helped with some very insightful reorganization that I think will improve what you are seeing today. And I'm going to be talking to you about how tropical storms form, and this short word "how" at the beginning really implies that we're thinking about understanding physical processes. So this is important because even if we have some kind of numerical weather model that can make successful predictions of storms 3 or 4 days in advance, we still want to understand physically what's going on. We want to have some insight perhaps into how the broad distribution of storms might change, why that might change over coming years or decades in response to, say, anthropogenic climate change. Much of this work was, a fair amount of this work was done by Michael Diaz, who was a postdoc here, who's now a research scientist at the Naval Research Lab down in Monterey. So I'm going to begin by showing you an extreme example of a tropical storm. This is Hurricane Florence over the just off the southeast corner of this image here. You're seeing a visible satellite image. The clouds are in white. And I'm playing this now, an animation of visible satellite imagery sort of interwoven with infrared satellite imagery. And you can see Hurricane Florence here. It's a vortex in the atmosphere. Air is flowing counterclockwise, we call it cyclonically, around the eye of the storm. This storm in particular made landfall in the Carolinas, where it was very damaging. It killed in excess of 50 people in the United States. That's pretty remarkable for a storm. It caused about $25 billion in damage. And this is perhaps no surprise when you hear that the peak winds in the storm were at least 150 miles per hour. And that's sustained winds. By sustained, they mean that if you measure the wind for a full minute, it doesn't drop below 150 miles per hour at its peak location on the surface. So for this talk, one of the main things I want you to note is that this storm, when it formed, was fairly far away from the US over the southeastern Atlantic. And indeed, if we go to my next slide, we can see, you see Africa here, and here is the early stages of Tropical Storm Florence. We name storms sequentially going through the alphabet. So the G storm has already moved out of the picture here, but the H and the I's, the disturbances, the atmospheric disturbances that would evolve into Tropical Storm Helene and Isaac, are marked here off the coast of Africa. And this is actually an image from a TV weather station. If you watch the Weather Channel routinely, you may have heard that many of the Atlantic hurricanes form from storms that actually originate over Africa. And you can see the two disturbances that are so disorganized and weak that they haven't even been named yet, are sort of forming here over this region of Africa. So what is it about the conditions here over the African continent that allows atmospheric waves or vortices to form there that eventually evolve into severe, extreme hurricanes in the Atlantic that affect the US? Well, to answer that question, I want to zoom out first and present to you the density of atmospheric vortices globally. This is made from an observational data product that takes all the available in situ and satellite observations of the state of the atmosphere, its temperatures, humidities, winds, and assimilates those into best guesses of what the atmospheric state looks like. We've taken those state estimates and applied algorithms to them to automatically detect the vortices that are present in the atmosphere and look at the track and characteristics of each vortex. What you're seeing here in shading is the density, the number of vortices per unit area, per unit time. And this region here over the Atlantic and over Africa is where most Atlantic hurricanes form. But you can see that that area is in no ways a global maximum. I want to actually, in the rest of this talk, focus on this area over Asia, because it is indeed the global maximum in the density of these atmospheric vortices. And this region right here is actually the home to what are called monsoon depressions, or in other words, when storms form here, when vortices form here, they are routinely called monsoon depressions. They are not called hurricanes. Typhoon is the name given to a hurricane that forms in the Pacific. And in this region, typhoons do sometimes form, but more often are these storms called monsoon depressions, which if you look at them, this is what one looks like. We have, just like Atlantic hurricanes, air moving counterclockwise around the vortex center. I'm showing you here the vectors show the wind about 2 kilometers above Earth's surface. Note the reference vector here has a magnitude of 20 meters per second. This corresponds to about 40 miles per hour. So you see the winds are, strong, but not that strong. They're certainly not 150 mile per hour like they were in Hurricane Florence. These particular storms are notable mostly not because of their peak wind speeds, but because of the massive amount of rain they produce. You can see that this color scale peaks at about 45 centimeters per day of rainfall. So these things that are called monsoon depressions, they bring a lot of the water that sustains India, Nepal, Bangladesh, South Asia in general. They bring a lot of that time mean rainfall. They also produce a lot of the floods that produce very large impacts in this very densely populated, socioeconomically vulnerable region of the planet. So we're talking about vortices that are in excess of 1,000 kilometers in diameter. The atmosphere is a 3-dimensional fluid, so these things have a 3-dimensional structure. And I'm showing you that structure here. One piece of it, at least, is a slice, a vertical slice through the center of the storm. So you're seeing plotted as a function of latitude and height, going from the surface up to 12 kilometers altitude. The temperature anomaly, the deviation in temperature in a monsoon depression from the typical state. And you can see that there's a cold region in the lower atmosphere and a warmer region above. These storms have a cold core. This is very distinct from hurricanes or typhoons, which tend to be warm throughout their entire center at all heights. I'm also showing you the eastward component of the wind, and that's what's contoured here in black. So eastward wind of 8 meters per second here, and negative eastward wind or westward wind here. So you're just looking here at the, you're getting the component of the vortex, the air spiraling around counterclockwise around the vortex center, which would be this vertical axis right here. So this is what a monsoon depression looks like, 3-dimensionally, if you will. And these vortices, what we want to know is, why do these vortices form with such high frequency over this region of South Asia? I'm showing you here a suggestion, at least one, the aspect that I'm going to explore in the rest of my talk that my group has been working on, which is that these vortices are spinning up in a region where the wind changes rapidly with latitude. So on this plot, you're looking at typical conditions over South Asia a day or two before the vortex of a monsoon depression can first be detected. Those storms typically form, they form most frequently over this sort of dashed black box region. And the vectors here show the wind at about 3 kilometers altitude. The color shading shows the eastward component of the wind. So it's red where the wind has a strong eastward component, and it's blue-purple where the wind has a westward component. So you see this strong shift as you move northward from strong eastward flow to weak westward flow. And just for orientation, if you weren't oriented already, this is India here, peninsular India. And these contours here, these black contours show topography. So you're seeing here the Himalayas, and this big blob is the Tibetan Plateau. So what I want to do is now move from observations to talking a little bit more about causation. What is going on with this sort of particular wind distribution, and why would it be important? There are a lot of other things about the conditions here over Asia that could be important for storm formation, such as the fact that the ocean temperatures are high, the atmosphere is very humid, other factors. But I'm going to focus in on that wind distribution. And first, I'm going to tell you a little bit about why it looks like it does. Why does that background wind, or the conditions a few days before monsoon depression formation, why does it have that typical distribution? So I'm showing you here a schematic of the planetary scale atmospheric overturning circulation. This, if you've had any kind of introductory earth science course, you'll know this is called the Hadley circulation. Typically, the planet is warmer in one region than in the other. If we happen to be somewhere near the solstice in, say, northern hemisphere summer, we'll have one summer hemisphere that's warmer, a winter hemisphere that's colder. Warmer air will be rising in the summer hemisphere. Colder air will be sinking in the winter hemisphere. And if we were on a planet that didn't rotate about its axis, then this would basically be what you get in terms of the circulation. But because Earth rotates about its axis once a day, there is a Coriolis force that generates eastward and westward flow. You can also think about this as being due to conservation of angular momentum about Earth's axis. I'm using here sort of classic physics notation of a vector going into the page or into the screen. You're seeing the tail of the arrow. Or here, the vector coming out of the page, you're seeing the tip of the arrow. These are your typical trade winds. If you've ever spent any time in Hawaii or the Caribbean or on most tropical islands, you'll know the wind tends to blow from east toward west. Except when you're in the summer hemisphere, near the equator, those typical trade winds get reversed to become what we call the low-level monsoon, sorry about that, the low-level monsoon westerlies or eastward flow. So the rotation of the planet gives us, the Coriolis force, conservation of angular momentum, gives us this change with latitude in the winds, the sort of planetary scale winds. And you're looking here at the slide that I showed you previously, you're looking at the local manifestation of those planetary scale winds over Asia. Now, what I want to show you is that there's a long tradition in the atmosphere and ocean sciences of thinking about the spin up of vortices or the amplification of waves as what we call hydrodynamic instability. And by this, we mean that you can have some kind of stable laminar flow distribution that will become disturbed if you perturb it by some very, very small amount. And I'm going to demonstrate that for you as sort of in this idealized analog of that wind distribution that I showed you previously that was observed over South Asia. This is a simulation of a two-dimensional fluid. We have the X and the Y dimensions here. You could think of this in terms of our atmospheric analog as X is the eastward direction, Y is the northward direction. And in this fluid, we have eastward flow in the southern part of the domain and westward flow in the northern part of the domain, just like we did over South Asia. And there's this strip here in the middle of dye that will allow you to visualize the flow better. And what we're going to do is just start the simulation. And what you'll see is that after a certain amount of time, this dye strip starts to undulate. I'm pausing it here. And what I want to emphasize is that this simulation was begun in this initial state by taking this very smooth laminar flow and perturbing it by putting in very, very small amplitudes of different wavelengths, of a lot of different wavelengths. And it turns out that one of those wavelengths amplifies faster than all the others. And it's this wavelength right here, where you can fit 3 or 4 waves in this domain. So that means there's a particular wavelength of a disturbance that's growing more rapidly than the others. Over time, that wavelength grows so much, it actually amplifies, becomes nonlinear into 4 vortices. Those vortices, some of them merge together, and the flow becomes turbulent and chaotic. But the key point here is to note that there was a particular wavelength that's been selected by the physics, the dynamics of the problem, wave number 4. And that was set here. We call that the least stable or the most unstable mode. Now, this is sort of my schematic to illustrate for you that atmospheric scientists, oceanographers think often as storm formation as that sort of hydrodynamic instability. So this is our sort of classic physical system analog. We think of a marble, a bowling ball, some sort of mass, either in a valley or on a hilltop. And it could have an equilibrium position. If you perturb it away from its initial equilibrium position, if you're in the bottom of a valley, gravity will just move you back toward the bottom of the valley, and maybe you'd oscillate about that position, but you wouldn't go further and further away from that initial condition. That would be a stable equilibrium. If you put in a small perturbation to your initial fluid flow, and you're using this physical analog here, a marble on the top of a hill, you can put in some small perturbation away from that initial resting point where you're balanced very carefully on the hilltop, and gravity will accelerate you further and further away from that initial position. You could also be in this metastable equilibrium state, or what we often call a finite amplitude instability. If we associate it with the finite amplitude instability, where you need to put in a certain amount of energy to get you out of that potential well. And once you've put in that amount of energy, in chemistry, we'd call this something like an activation energy, then you could accelerate away from your position even further, sort of spontaneously. So we're thinking about our system here being a sort of unstable equilibrium state. And what I'm going to do now is go back and take this observed wind distribution. And now, instead of just looking at the observations in a diagnostic sense, we're going to put this into a numerical model of the equations for fluid flow. These are just 2 examples of 2 of the equations. The equations that I'm talking about are the Navier-Stokes equations, or various simplifications thereof. We have conservation equations for momentum, for energy. There's also conservation equations for mass, and we'll have water conservation equations too. And we're then going to look at what the structures are of the disturbances that grow most rapidly out of this initial state. When we do that, we actually can see that this is the disturbance that you get that grows most rapidly. For those of you who might be familiar with this, this is actually the gravest eigenmode of the system. It's the least stable linear mode. What we have here contoured is in colors, it's the pressure anomaly. We have a low pressure region here, a high pressure region here. And the vectors show you the anomaly in the wind at about 3 kilometers altitude. You can see here peninsular India here, the northern Indian Ocean, Bay of Bengal is this region right here. And these black contours just show you the background wind where it changes from being eastward, contoured in solid black, to being westward, contoured in dashed lines, just for reference. So this is the structure of that least stable, the most rapidly growing disturbance, the least stable mode on day 0. This mode actually evolves in time. And so on day 2, 2 days later, this pressure anomaly has intensified and you have flow moving counterclockwise around that vortex. And it is the pressure anomaly, the vortex, has actually moved toward the west. We go 2 days later, it's intensified even more and moved further toward the west or northwest, very similar to the observed monsoon depressions over India. And we go through sort of a life cycle where it keeps moving to the northwest and then its intensity dissipates. So I can now show you that this is what happens, this is your series of snapshots. But I can actually show you an animation, and I'll introduce another complication, which is that we will allow water to condense and to form clouds. When we do that, you're seeing here pressure anomalies in color contours, wind anomalies in vectors, and additionally now you're seeing rainfall as these color shading, as a color shading here, with the color scale chosen to be somewhat similar to what you'd see in a weather radar. So we see this vortex sort of amplify as you reach the northern Bay of Bengal and propagate to the northwest over India, dumping a lot of rain as it goes. The interesting thing is that the structure, the propagation, the wavelength that's growing is actually very similar to the more simple calculation from the previous slide, where we actually didn't allow water to condense. So the dynamics here, in the absence of water condensation and phase change, we're arguing, setting the basic structure and propagation of the storm. Now, what we can do is actually use the equations of fluid motion to ask the question of, well, where does the energy of the storm come from, right? This is a vortex that's amplifying. Its kinetic energy is increasing. And what we're going to do is look at a budget, if you will, for the kinetic energy of that storm. What I'm plotting here are 2 processes that are generating kinetic energy for that storm. And this kinetic energy generation rate has units of joules energy per cubic meter per day. And we're seeing here the kinetic energy generation due to friction. It's negative, as expected, due to the fact that friction typically dissipates kinetic energy. And friction is opposed by this term here, which is the conversion of kinetic energy from the background eastward wind into the kinetic energy of the storm itself. So I put up here, again, my schematic here. This is the background wind out of which the storm is growing. This strong eastward wind over the southern part of India and the northern Indian Ocean, this has a certain amount of kinetic energy to it. You're looking here at the kinetic energy associated just with the vortex. So it's sort of the perturbation kinetic energy about this initial state. And what's happening is the storm is growing by extracting kinetic energy from this background state and converting it into the rotational kinetic energy of the storm. So this eastward wind is weakening and the vortex is intensifying. And that's really, well, sorry, before I jump to the summary, I wanted to just say that this is not the only place that the kinetic energy could come from. There are many other possibilities. For example, for a hurricane in the Atlantic or a typhoon in the Pacific, we know that a lot of the energy comes from ocean heat content. For mid-latitude storms in the United States or in Asia, and pretty much anywhere in the mid-latitudes, like severe winter storms, blizzards in the northeast of the US, they actually get their energy primarily from potential energy of the atmosphere, in particular, the cold and dense air up near the pole sort of slumps down and spreads out across the surface of the planet, attains a lower potential energy state, and the potential energy it lost goes into the kinetic energy of those winter storms. So here we have a very particular source of the kinetic energy for the storms, which is the kinetic energy of this planetary scale wind, which I illustrated for you back here, is associated just with this planetary scale overturning circulation and the trade winds and the low-level monsoon eastward flow. So that's all that I have for you today. I want to leave, I've left hopefully some time for questions. Just jumping to the end, my summary is that what I said at the beginning, if we want to make short-term predictions of individual storms or long-term predictions, say, as a consequence of anthropogenic climate change over the next century, how the statistics of all storms will change, we really need to understand how these storms work. What is their fundamental physics? And there is a long history, well over 50 years, of using hydrodynamic instability theory to explain the physics of the amplifications of vortices and waves in both the atmosphere and oceans. And the finding that I presented to you in particular today has to do with monsoon depressions. These are sort of, some people have thought of these as kind of proto-typhoons or proto-tropical cyclones. They're weak in terms of their wind speed, but they produce abundant rainfall that's societally very important for well over 1 billion people that live in South Asia. They're interesting geophysically because they form over this pretty small area of the North Indian Ocean, a vast region that's pretty warm and moist, but their genesis frequency peaks over a pretty small confined area of that warm and moist region. And our arguments, our discoveries, if you will, has been that these storms really owe their existence to latitudinal gradients in the background eastward wind and the particular instabilities that arise from that. So maybe just last closing thing is that one thing I'm doing as part of my Miller professorship is to ask the question of what role barotropic instability, that particular type of instability, plays in setting this global distribution of storm occurrence, and how will that change as a function of climate state. So I will end there and happy to take any questions.